Hello everyone, I'm Navin Sriram and a Robotics Institute Summer Scholar for the year 2025 from the Indian Institute of Technology Madras. And this summer, I've worked on real-time resilient planning by multimodal reasoning, along with Andrew Jong, Jai Bhatrikar, and Sebastian Scherer as a part of the Air Lab. With robots being deployed in the real world in different environments, structured, unstructured, indoor and outdoor, they face varying risks during their operation. If we look deeper, these risks are often of two types. One which will undoubtedly lead to failure, for example, things like fire, which is mostly true if not always for all kinds of agents. But on the other hand, some risks appear less frequently, which might be safe for some agents and risky for some, stemming from our earlier view where we say that safety is relative. For example, a bed floor might be dangerous for a mobile robot, but not for a drone, which is common sense, but even within mobile robots, it might affect two different robots differently based on the traction system. So out of distribution risks are ambiguous and present at the long tail of the risky scenarios. Some recent works on identifying and mitigating out of distribution risks have been published. Let's look at them. This latest work from Stanford tries to address the problem of out of distribution risk mitigation through multimodal reasoning. Their workflow is composed of two pipelines. The first one is where the robot sends its current observation as an image, prompting a large vision language model to identify possible risky scenarios in the captured scene. The VLM returns a list of objects and scenes, and the robot assigns safe and unsafe sets to look out for. Is this even out of distribution risk mitigation? If such a risky scenario could be found visually and preemptively, is this truly out of distribution? This becomes mere association with no foresight into the actual effect on the robot. We want to present a potentially better methodology to identify and mitigate such out of distribution risks. Motivated by principles of resilient planning, we propose experience driven risk assessment versus long tail causes. When a robot faces some unknown risk, we reason post hoc about possible causes from the environment, associating these anomalous behaviors with semantic features. We start with a known set of deterministic and common dangers and update the risk library dynamically to account for out of distribution risks on the fly, creating an informed dynamic risk library. Our approach assumes the robot has a pre-planned path with low-level control and is good at collision avoidance. For now, we treat risk simply as a trajectory tracking error. We run the robot first on a known trajectory without risk to calibrate the nominal drift values to reduce false positives. The entire proposed pipeline is split into two different parts operating at different frequencies. The fast loop operates in real time using dense open vocabulary semantics to look for semantics corresponding to risky objects and already present in our dynamic risk library. Once a robot encounters an anomaly, we trigger the slow reasoning loop in parallel, where we backtrack and narrate the experienced behavior to a vision language model with an image of the scene taken before the risk was encountered. The vision language model now answers back with a textual description of the cause, which we encode using a language encoder, creating a detailed summary of the experience, which we store in the dynamic risk library with the index being the cause embedding. In the fast loop, the robot operates at real-time speed, continuously extracting dense, language-aligned semantic features from the live camera input using the NaRADIO and SigLIP pipeline. Each pixel in the scene is mapped into a rich embedding space, allowing the robot to segment out objects and regions based on open vocabulary text labels without needing prior training on specific classes. The robot compares these features with entries in this dynamic rest library, searching for semantics that match previously encountered hazards. Risk detection is performed instantly by monitoring the trajectory tracking errors. If the robot deviates from its nominal path, this triggers anomaly logging. When an anomaly is detected in the fast loop, the slow loop activates to perform deep reasoning and continual learning. The system buffers multimodal sensor data, camera frames, post information, semantic maps leading up to the event. It then narrates this experience to a large vision language model, which analyzes the context and provides a causal explanation for the unexpected behavior. If the cause is new, its semantic embedding is generated and added to the dynamic risk library. These embeddings, along with metadata and risk-given information, are indexed and clustered in real time using a FAISS-powered database. To make risk assessment predictive, the system fits a risk Gaussian process. This models how observed disturbance is related not just to physical distance, but also to semantic similarity, enriching future risk prediction and enabling adaptation to previously unseen hazards. So here's a small trial on the Ascent Spirit coaxial drone to validate our pipeline. Here we use a ZX camera connected to an ORINAGX payload used for logging observations, and we use the internal visual inertial odometry pipeline to capture the pose required for the anomaly detection framework based on nominal and actual trajectories followed. So we play recorded ROS from the drone, and as we move the scene, we see that the drone is approaching this fan, and as it moves ahead, it gets drifted to the right. And this immediately triggers the anomaly detection pipeline, which also triggers the narration subsequently, which creates a narration based on the deviation and the nature of the deviation. So it says, I was trying to go straight, but I suddenly drifted right. This is sent to the vision language model, which operates asynchronously, which listens to the cause and generates the answer, which is the fan, which the robot receives. So the next time it sees a fan on the right over here, it knows that it is a risk object and is ready to detect it and deploys countermeasures. In our evaluation, we move beyond standard benchmarks by using a self-supervised experience-driven framework tailored to each robot embodiment. When the robot encounters unexpected disturbances, its exploration policy actively adapts, focusing on unexplored or high-risk areas discovered through its own experience. As the robot accumulates anomalies and tracking errors, it builds progressive data-driven risk heat maps that reveal true out-of-distribution challenges, rather than relying on static and incorrect ground truth risks. Our methodology is validated across multiple platforms and randomized physical properties, demonstrating robust adaptive out-of-distribution risk detection that's truly agent-specific and continually evolving. Thank you.